Hello, everyone, and welcome to the 2022.
No, we're good.
Oh, we're good. Okay, we thought for a moment we had no sound. Welcome to the 2022 Algebra 1 Regents Review. My name is Kirk Weiler. I'm here representing eMATH instruction, and we've got a phone in the frame. That's why we didn't have it that high. Anyway, we're streaming on both YouTube Live, the eMATH instruction channel on YouTube Live. That is so cool looking. And on Instagram Live, which is why there was a phone in the screen right there. Thank you, Joey. Joey, my producer, everyone. Yay! I want to have like then the band, the orchestra guy that I turn to who gives me that funny quip or whatever. Anyway, we're here for the June 22 Algebra 1 Regents Review. And what we're going to be doing tonight is we're going to be going through the June 2021 Algebra 1 Regents exam from the first question to the last question. I'm going to be utilizing the TI Inspire tonight in order to do the calculator work. If you're working on, the TI 83 or 84, or a Casio or something like that, I'm sorry. Hopefully, you'll still be able to follow along with what I do with the calculator, and you'll be able to extend it to what you're doing as well. So let's get right to it, and let's jump in and start with the multiple choice problems on the June 2021 Algebra 1 Regents exam. Now, I'm sure that many of you have done practice Regents exams at this point, all right? But there's something like, I don't know, 20, you'd think I'd have this memorized, 24 multiple choice questions to begin, all right? There's no partial credit on them. There's only one right answer per question, all of that good stuff. So we're gonna go through them one by one. When we have to bring out the calculator, we will, but I don't think we have to on the first one. So let's take a look at problem number 1 on the exam. A high school club is researching a tour package offered by the Island Kayak Company. The company charges $35 per person and $245 for the tour guide. Which function represents the total cost, C of X, of this kayak tour package for X club members? All right, so by the way, I would really advise you having a copy of this exam on hand. It makes it a lot easier if you're kind of working at it. You can get a copy of that by going to the New York State Education Department, by typing into Google Algebra 1 Regents exams, or by going to eMATH instruction, going to our May newsletter. We also have this test posted. Anyway, let's get back to problem number 1. All right, we're trying to figure out which one of these 4 functions properly models what's going on. Now, hopefully this looks pretty familiar, right? We've got $35 per person, right? That's a rate. And then we've got this thing here, $245 for the tour guide. That's what's known as a fixed cost. In other words, it doesn't matter whether one person goes on this tour or 100 people go on this tour, we're going to have to pay $245 for the tour guide. So this is a classic y equals mx plus b situation where the 245 is our y-intercept and the $35 per person is our slope, and therefore our answer is choice 2, right? Y equals 35 times x plus 245. And I'm sorry if the screen is a little bit difficult to read. I know it's a little bit washed out. I wonder if I should actually try to adjust the lighting on that. What do you think, Joey? Should we take a moment, try to make it darker? Give me just a moment, everybody. I'm going to try to make the screen just a little bit darker for you. All right. Yeah, I like it. Okay, that looks better. Hopefully that's just going to go away in a second. Maybe, maybe not. Okay. I'm good. How about close? No? Yeah, it should just go away. There we go. All right. Ta-da! Technology. All right, let's move on to problem number 2. The expression 3 times x plus 4 minus the quantity 2x plus 7 is equivalent to which of the following? All right, so we've got a couple things going on here. We've got a little distribution multiplication by 3 here, and we've got to subtract a binomial. And keep in mind, anytime you're subtracting a polynomial, a multi-termed expression, The way you want to do the subtraction is to simply change the sign on everything inside of the parentheses and add instead. So what we're going to have, right, when we do 3 times x plus 4, we're going to have 3x plus 12. Then when we distribute that -1, it's going to be plus -2x and plus -7. Now I can use the commutative property of addition to sort of just do a little rearranging here so that I get my x terms near my x terms and my constants near my constants. I can now combine these like terms. 3x plus -2x is a positive x, and 12 plus -7 is positive 5. And so my correct answer is choice 1. All right, so combining a little like terms, doing a little distribution, good enough. Let's take a look at problem number 3. A function is defined as k of x equals 2x squared minus 5x plus 3. The value of k of -3 is which of the following? Now, this is a classic function problem called function notation. And the idea is we're looking for the output when the input or the x value is -3. So in theory, very easy thing, very easy mechanically the idea, right? We're going to put a -3 wherever there's an x and we're going to evaluate this function. Now, I'm all for doing arithmetic in your head, and we could certainly work this all out sort of in our head, you know, without a calculator, but I think this is a great time to bring out the TI Inspire. Now again, I'm simply going to go into my calculator, all right? Now, I could just, you know, put this expression in. I could write this in exactly the way it looks, and I could get whichever answer there is. But let me show you something really kind of cool on these calculators that's really awesome and allows you to do a problem like this very simply, and we're going to use it a little bit later on too. Right above the var button, that might not go so well, right above the var button here, all right, is the word STO, store, all right? And what I'm going to do is I'm going to take -3 and I'm going to store it in the variable x, and I'm going to hit enter. Now, right now, my calculator thinks the variable x is equal to -3. Now, don't get me wrong, that doesn't affect graphing or anything like that. But while I'm on this page, x is equal to -3. So if I typed in something like x plus 2, it tells me -1 because -3 plus 2 is -1. If I typed in 4 times x, it would tell me -12 because 4 times -3 is -12. But what I want to do is I want to type in the following. And I've got to minimize this. Oh, good, it still worked, right? So what I want is I want to type in 2x squared minus 5x plus 3. And look at that. It tells me 36. So in other words, the store function is wonderful when you're trying to evaluate an expression for a particular value of x, and it could actually have multiple values of a variable in it. All right, you could have x, y, all sorts of things, and you can then just type it out after you've stored those values in it, and it will give you the correct value. So right now we're talking about a value of 36. Whoops. All right, choice number 2. All right, let's take a look at problem number 4. This one's going to be quick. Which relation is not a function? All right. So functions are all about taking numbers in a set called the domain, inputs, x values if you want, and making them into numbers in what are called the range. They don't have to be numbers, they could also be letters and stuff like that, but things in this range or the y values. And the golden rule for a function is that a single x value can only go to one y value. Now, multiple x's can go to the same y, but a single x can only travel to one y. So I'm looking for something here that violates that. It's like, okay, that didn't work. And it's choice 4, right? Because in choice 4, the number 6, and it's always these things are the inputs, the sets on the left, right? The number 6 goes to both the number 10 and the number 12, and because of that, it is not a function. All right, let's move on to page 2. Okay, number 5, let's take a look. The value of Tony's investment was $1,140 on January 1st. On this date, 3 years later, his investment was worth $1,824. The average rate of change for this investment was $19 per day, month, quarter, or year. All right, now this is a really interesting average rate of change problem. Pretty much always when you're given an average rate of change, you're given like sort of two values and then the time interval or something over which it's changing, and then you're just sort of asked for the rate of change. They want to know kind of what this rate of change is in terms of, is it $19 that you're earning every day, every month, every quarter, every year, okay? And by every quarter, what they mean is a quarter of a year. Well, first things first, let's just see how much his investment, Tony's investment, went up. Now, we can do that by taking the final price, $1,824, and subtracting the initial price, $1,140. And we'll do that real quickly on our calculator. Let's see, 1824 minus 1140. I really could use this to be a little bit smaller. Thank you, calculator. And we get 684. 684. Now, remember that $684 was over the span of 3 years, all right? So let's divide this by 3 years. And what we find out when we do that division is that that was $228 per year. All right, so clearly we're not having an average rate of change of $19 per year. We're not having that, right? Because if it was $19 per year, right, then that's what this calculation would have turned out to be. But it wasn't, right? It was $228 per year. Now, if I wanted to know how much it was per quarter, I could take this number and divide it by 4, and that would tell me how much it was per quarter. Let me just see how much I made per quarter. I'm going to take that 228, I'm going to divide it by 4, and that means I made $57 per quarter. Still not what I'm looking for. I'm looking for $19 per something. Well, if I made $228 per year, let me divide this by 12 now. Right, 12 months in a year. Ah, there it is. There's my 19, right? So if I'm making $228 per year and I divide by 12, right? What I'm really doing here is kind of a unit conversion. I've got $228 per year, and then I multiply by 1 year per 12 months, right? The years cancel, divide by 12, and we get $19 per month and no room to do our next problem. But we're going to have to get rid of some of that writing. I hope you write smaller than I do on the Regents. This is the space you have to work, though. Really important. I think it's time for my first sip of lemonade. Oh, I'm going to need that all night tonight.
2,300 people watching.
2,300 people watching. You know, most of them are just my relatives, but I'm kidding. I have a very small family. Anyway, and gosh only knows on Instagram. So, all right, so what we've got now is $19 per month, a very atypical average rate of change problem in that you actually have to figure out the interval of the change, which is strange. Now let's take a look at a much more standard problem in number 6. The solution to 3 times x minus 8 plus 4x equals 8x plus 4 is which of the following? All right, so this is just a straight up solve this algebra problem. I'm going to have to get rid of all of this, otherwise I'm going to have no room to write. Let me just see. I can't do a lasso. I was hoping, but didn't happen. All right, there we go. All right, so first things first, let's do a little bit of distribution on the left-hand side. We're going to get 3x minus 24 plus 4x is equal to 8x plus 4. Now on the left-hand side, we're going to take that 3x and that positive 4x, and we're going to combine them to get 7x. Now, I don't know about anybody else. I'm a big fan of getting my variable on the left-hand side, so I'm going to subtract an 8x from both sides, and my magical red pen is just going to show up. I have to watch out a little bit here. 7x minus 8x, negative x, and minus 24 is equal to 4. I'm going to add 24 to both sides to To get rid of that negative 24, I'm going to have negative x is equal to positive 28. I could divide both sides by negative 1 if I wanted to, but if negative x is equal to positive 28, then positive x is equal to negative 28. And there we have it. Choice 4. All right. And again, not enough room. Not enough room. Let's take a look at number 7. I definitely need to get rid of this for this now. All right, hopefully everyone saw that. Great. All right, here we go. Man, I gotta start writing smaller. All right, number 7. An ice cream shop sells ice cream cones, C, and milkshakes, M. Now, of course, C is the number of ice cream cones, and M is the number of milkshakes, and shame on them for not making that more clear. Anyway, each ice cream cone costs $1.50 and each milkshake costs $2. Donna has $19 to spend on ice cream cones and milkshakes. If she must buy 5 ice cream cones, which inequality could be used to determine the maximum number of milkshakes she can buy? Okay, so let's get it all out here, right? You know, we've got these two variables, right? The number of ice cream cones, C, and the number of milkshakes, M. Got it. We know the price of each, so we got 150 times the number of, ice cream cones cost 150. Those are cheap ice cream cones. Ice cream cones cost 150 and milkshakes cost $2. I want to go to this place. Even our local ice cream place, Holy Cow, and shout out to Holy Cow, has low prices, but not that low. Anyway, Donna's got these $19 to spend. So obviously, you know, if we take the number of ice cream cones and multiply it by 150, plus the number of milkshakes and multiply it by $2, right? And add those two together, that's going to be our total cost, right? So let's just take a look at that, right? So if I just said, you know, 150 times C plus $2 times M, that's my total cost. Now, one thing I know for certain is that must be, my total cost must be less than or equal to 19, right? So that would really be the inequality that would model everything that was going on in this problem. But then they go on to say Donna has to buy 5 ice cream cones. She has to. So C is no longer a variable, right? C is now a fixed number, and specifically C must be equal to 5. So, right, 150 times 5 plus 2.00 times M must be less than or equal to 19, right? And where is that? Right here. And they try to do everything they can. They throw the greater than or equal to 19 in there, which meant you could buy as many ice cream cones as you want, or as many milkshakes as you want. You must buy 5 ice cream cones. You know, and then of course they do the switcheroo on where the 5 should go. Should it be multiplying 150 or multiplying 2? But that's just keeping track of which one you have to buy 5 of. And in this case, 5 ice cream cones. All right. Let's get into a little bit of binomial algebra, number 8. When written in standard form, the product of 3 plus x and 2x minus 5 is which of the following? All right. I love the fact that they put this little wrinkle on and they wrote it as 3 plus x instead of x plus 3. Addition is commutative. Now, if that was subtraction, 3 minus x, this would play out a little bit different. But the first thing I'm going to do is I'm going to write this thing as x plus 3. Again, that works because it's addition and not subtraction. I could never rearrange that second one. I could never make this one into 5 minus 2x. That would be incorrect. All right, I could make it into negative 5 plus 2x if I wanted to, but that's different. Now, you should have multiplied out binomial after binomial after binomial when you were doing, you know, Algebra 1, okay? I'm going to use the FOIL method, the first, outer, inner, last method, and I'm going to come back to that method 2 problems from now when we do number 10. But, right, when I do my FOIL algorithm, right, the first thing I'm going to do is multiply x by 2x, and I'm going to get 2x squared, right? Then I'm going to do my outer 2 terms, negative 5 times x is negative 5x. My inner 2 terms, 3 times 2x is positive 6x. And then my last terms, 3 times negative 5, which is negative 15. The only 2 that will ever combine will be the O and the I. That'll be 2x squared, negative 5x, positive 6x is just positive 1x, and then minus 15. So that's going to be choice 2. Now, before we move on, we're going to lay a little groundwork for problem number 10, and then we'll just have to do problem number 9 in between. Notice that whenever you FOIL, right, assuming that these two terms don't cancel each other out in the middle, the first term of this binomial times the first term of that binomial ultimately is what gives you this term, right? And then the last term times the last term is what gives you these terms, this term, right, the constant. It's that O and the I that combine in the middle to give you that x to the first term. And that's going to become important when we do number 10. But first, let's take a look at number 9. If x equals 2, y equals 3 times the square root of 2, and w equals 2 times the square root of 8, which expression results in a rational number? All right, so let's get to the meat and potatoes of this, right? You got lots of different types of numbers, okay? Rational numbers, irrational numbers, integers, whole numbers, positives, negatives, fractions, decimals, all sorts of numbers, right? Rational numbers, right, are those numbers that are generally quote unquote nice. They're numbers that have decimals that either terminate or that repeat in some kind of a pattern, all right? Irrational numbers are like the really messy ones, right? Those have those decimals that go on forever and they never repeat and they have no pattern or anything like that. Like pi is a good example, but so are any square roots of non-perfect squares. So things like the square root of 8, that is an irrational number, and 2 times the square root of 8, that's also irrational. 3 times the square root of 2, that's also irrational. The number 2, however, x equals 2, that is a rational number, right? Because that's just like 2.0 and it stops, right? Or 2 point and it stops, however you want to look at it, okay? So the thing is, in Algebra 1, you're supposed to learn all these rules. Like when you add a rational number to an irrational number, you get an irrational number. On the other hand, when you add an irrational to an irrational, you could get a rational or an irrational. It all just depends. When you multiply a rational number by an irrational number, you get an irrational number. But when you multiply 2 irrational numbers, you could get a rational number. Oh my God, right? Oh my God. So one way of doing this problem that's really rather nice is on our calculator. Shocker, okay? And before I kind of get into this on the calculator, I'm going to kind of go in here for a second and I'm going to noodle a little bit with my settings. So one of the things about my settings, all right, oops, no, there we go, jeez. Okay, bail calculator, bail. Okay, all right, yeah, you're good. No, you're not good. Oh my gosh. Oh, I don't even know. I'm just like, yeah, okay. I think it's done. I don't even know what I'm doing anymore. All right, so anyway, I was going to change the number of decimals it showed. I'm pretty sure it's where I want it right now, which is float 12. I want it to show as many decimals as it can, because remember, irrational numbers go on forever. This thing has a life of its own, this online calculator. So I'm going to use that store command again. Remember the store command that I showed you? Except this time I'm going to store a bunch of stuff. I'm going to take 2 and I'm going to store it in x. All right, then I'm going to take 3 times, I couldn't find the square root button, it's so tiny. 3 times the square root of 2, and I'm going to store that in y. Aha. And then I'm going to take 2 times the square root of 8, and I'm going to store that in w. You just couldn't go with z, could they? All right. Now here's the cool thing, and by the way, again, notice those very, very messy long decimals. If we could really zoom in, you could see that they were, they don't repeat or anything like that, all right? In fact, right, kind of maximize it, right? These things are definitely irrational numbers. Now the cool thing is, I can now type in all of those expressions and see if they turn into either sort of nice numbers or not so nice numbers. Like the first one, x plus y. I literally can just do x plus y, enter. That's a long, messy, never repeats number. That's irrational. I'm looking for the one that's rational. That's irrational. So now they've got y minus w. Oh, another real long, messy, ugly answer. The next one is w times y. W times y. Let's take a look. W times y. 24. 24. There it is. There's a nice rational number. Now let me show you why it's rational real quick, but that's the answer, okay? But the reason why it's rational is W is 2 times the square root of 8, y is 3 times the square root of 2. I can now write that as 2 times 3 times the square root of 8 times 2, because these are both under square roots, I can put them under one square root. That becomes 6 times the square root of 16, but the square root of 16 is 4, and therefore my answer is this nice rational number 24. Right? That's it. Now again, the thing that they're trying to test you on in this problem is all of those random rules about, adding a rational to an irrational. That's what's going on here, at least in number 2. Then we've got 2 irrationals that subtract, which, by the way, could have been a rational number. It wasn't in this case. And this last one, again, would have also been irrational. In that case, we would have had a rational number or an irrational number divided by a rational number, which gives you an irrational number. I think learning all that stuff is completely irrational, so let's move on to the next problem. Number 10. Which product is equivalent to 4x squared minus 3x minus 27? All right, so when we look at this problem, ultimately what they're asking us to do is to factor this, except they've given us the 4 choices. We just have to figure out which one's correct. Now remember, okay? Really, what you'd ideally do is you'd multiply out each one of these 4 to see which one then was equal to 4x squared minus 3x minus 27. But you don't have to do that. In each one of these choices, the first 2 terms, 2x times 2x gives me 4x squared, 9 times negative 3 gives me negative 27. The first and the last terms are going to work out just fine in each one of these 4. Now you should glance and make sure that's the case, but it is in this situation. So all we have to do is just check out the O and the I of FOIL and see if they combine to give us the negative 3x. That's all we have to do. We don't have to do the whole thing. We don't have to do the 4x squared and the negative 27. That's going to work out on all of these. So let's do the FOIL, right? On this first one, we have 9 times 2x, which is 18x, and we have 2x times negative 3, which is negative 6x. Those two combine to be 12x, and that's not what I need. I need negative 3x. Let's try number 2. In this case, we've got negative 9 times 2x, which is negative 18x. Then we've got 2x times positive 3, which is positive 6x, which is negative 12x. Again, not what we need. That doesn't look like a negative. Let me make it look a little bit better. Equals negative. There we go. Negative 12, not what we need. We're looking for negative 3. Let's take a look at the next one and get rid of all this radical work. I've got 9 times x, great. And I've got 4 times negative 3, which is negative 12x. And 9x minus 12x is negative 3x. And that's my winner. If I had done choice 4, I would have found that the two combined to be a positive 3x, and that would have been incorrect. That's it. That's all we had to do. All right. Time to pause for a moment and have a word from our sponsors, the Lemonade Council of America. Lemonade, a drink that is 98% water, 1.9% sugar, and 0.1% lemon juice. Oh, so good. So good. All right, let's take a look at number 11. It's the only thing keeping me going. All right, given f of x equals 2/3 x minus 4, and g of x equals 1/4 x plus 1, 4 statements about this system are written below. Statement 1, f of 4 equals g of 4. Statement 2, when x equals 12, f of x equals g of x. 3, the graphs of f of x and g of x intersect at 12, 4. 4, the graphs of f of x and g of x intersect at 4, 12. All right, now, We could solve this system algebraically, absolutely, by setting this equation equal to this one. But a couple things, right, before we kind of get into how we're going to do this using the graphing calculator. Number one, when you see f of x and g of x, what I want you to think of is just the variable y, because that's what they are. They are y. That's all they are, okay? So when you see something like f of 4 equals g of 4, what that says is that when x is 4, the y on this graph is equal to the y on that graph. Here, when x is 12, it's saying the same thing. The y on this graph is equal to the y on that graph. They just don't have the 12 sitting inside of the parentheses that time. Okay, so this is f of 4 equals g of 4. This is f of 12 equals g of 12. And I think we know what it means for a graph to intersect. So let's take a look. Let's actually just solve it graphically on the graphing calculator. In fact, I'm going to go over here. I'm going to go down. Let's throw a graph in. All right, in F1. I think I'm going to even use my fraction bar. I'm going to put in 2/3 x, that looks good, minus 4. Hit the down arrow. Now I can put in g of x. Again, I'm going to use my fraction bar. 1/4 times x plus 1. Make sure I have it correct. Enter. Now, one of the things I noticed, right, is that these two lines are going to intersect, but they're going to intersect somewhere over here, right? So I got to like fiddle with my window a little bit. I'm going to go into menu. Choice 4 is window. I'm going to go into my window settings. My X-min is fine. I mean, I could change it. Oh, no. No. Bad calculator. Bad calculator. Okay, do not use the tab button, Kirk. Do not use the tab button. Okay, I'm going to make that 20 and hit enter. Okay, good. Okay. One of these days, I'm not going to be able to get out of it. It's just going to go on this infinite cycle. I'm going to have to like close the program, restart my computer. There's my intersection point. Let's use the intersection command on our calculator. Hopefully you've done that before in this course. I'm going to go into menu. I'm going to go to analyze graph. I want my intersection point. Looks like I need to drag this line somewhere to the left of the intersection. I'm good. I hit enter. Now I drag it to the right. I hit enter. And my intersection point, this is very small, let me enlarge it. My intersection point is at 12, 4. And that is absolutely key, right? When x is 12, y is equal to 4. Got that? When x is equal to 12, y is equal to 4. Let's take a look. All right. When x is equal to 12, right, y is equal to 4, the two y's are equal. All right, so this is definitely the case. All right, as well, the one that we definitely know is true, the graph of f of x and g of x intersect at 12, 4. I mean, we had that just immediately, right? This one has to be part of it. So given that 3 has to be in the choice, it's got to be choice 4. But again, these two are really saying the same thing. Choice 2, choice 3. All right. Oh, let's take a look at one where they really went all out to produce beautiful graphs for you. Number 12. Which sketch represents the polynomial function f of x equals x times x plus 6 times x plus 3? All right, now, just for a moment, let's pretend we can't just put this in our calculator and produce the graph. We will do that in a moment. But for right now, I just wanted to mention that when you look at this, immediately you should know that these two are wrong. All right? These two graphs are not functions. They fail what's called the vertical line test. Anytime a vertical line goes through a function more than once, anytime a vertical line passes through the graph of anything more than once, it's not a function, okay? It means that a given x, this particular x value, has 1, 2, 3 y values, not a function. So that one can't be right. So it's either this one or this one. Neither one of these two can be right. Now, which one is it? Well, what they really want you to be doing here is thinking about what's called the zero product law, or the correspondence between factors and zeros. In other words, if I took this and I set it equal to 0 to find the x-intercepts, right? This finds the zeros, or another way of putting it are the x-intercepts, right? Then what happens is I take each one of these things and I set it equal to 0. This one's done. This one gives me -6 as an answer. This one gives me -3 as an answer. So my three x-intercepts have to be 0, -6, and -3, and that happens to be this graph. Now, there's absolutely nothing wrong with just throwing it into your calculator. Although I did find one little quirky thing. I'm just going to real quickly go to new. No, I'm going to add a graph. So one thing I found that was very, very odd about this is, if you try to put it in, and I don't know why this is the case on the TI, I'd love to figure this out. If I put it in exactly the way it looks on the paper, uh-oh, that's not what I wanted. Man, let's try that again. X times X. Do not resize the graph. So if I do this, it gives me an error. Really weird, really weird. So, by the way, I still can't quite figure out why that happens, but if I put a little multiplication between the x and the x plus 3, then it's golden. It's good to go. No idea. Very strange. But anyway, and apparently I can zoom in that way. So, you can immediately see just by basically putting it into the calculator that it is in fact this graph. But the bigger picture, right, is if you have a polynomial that is factored like this, right, it's written as a product, x times x plus 6 times x plus 3, you can set that product equal to 0, set each one of the factors equal to 0, always gives you a very easy equation to solve, and that then gives you the x-intercepts of the graph. All right? All right, x-intercepts of graphs. Let's keep it going. Here we go. All right, problem number 13. Let's take a look. If the parent function of f of x is p of x equals x squared, then the graph of the function f of x equals x minus k quantity squared plus 5, where k is greater than 0, would be a shift of blank. Okay, this is a pretty wordy question, but here it's all about what are called horizontal and vertical shifts of functions, and specifically horizontal and vertical shifts of the parabola y equals x squared. So again, forget about p of x, right? Just y equals x squared, right? If I gave you something like, if I gave you something like this, y equals x minus 5 squared plus, let's say, 11, and that fits sort of what they're getting at here, except I should have a plus 5 out here. The idea is that we took this thing, and because we subtract 5 from it, that shifts it 5 units to the right, which is a little weird, because you'd think that if you added or subtracted from x, if you added, you'd think it would move it to the right, and subtract, you'd think it would move to the left. But that is, in fact, not the way it actually works, right? If you subtract a positive number directly from x, it moves it to the right. If you then add directly to the function, it does in fact move it the way you'd think it would, which would be shifting it up. So in this case, when we don't have a 5, but we have a k, you would think I have never worked on this before, then what's going on, because k is greater than 0, and they have to tell you that, what's happening is we're shifting k units to the right, and we're shifting 5 units up. So k units to the right and 5 units up. And again, if you're confused about that, I would encourage you on a problem like this, remember you have 3 hours on the algebra exam. Put y equals x squared into your calculator. Put this thing in, but choose a value of k. Don't make it 5, right? Choose k equals 3, k equals 10, k equals whatever, and see what happens. All right, let's take a look at number 14. Which expression is equivalent to the quantity -4x squared to the third? All right, whenever we have a monomial, a single term, inside of a parentheses being raised to a power, we can take each portion of that monomial and raise it to that power. In other words, what I can do with this is I can take -4 and raise it to the third, and then take x squared and raise it to the third. Now, -4 to the third is -4 times -4 times -4. And obviously, if you need to, you can take your calculator out and figure out what that is. I know it's -64. Now, x squared to the third, you're supposed to know that what you do is you take the 2 and the 3, and you multiply them together, and you get x to the 6th. You do not add them. That's if I had like x squared times x cubed. So negative 64 x to the 6th, there we are. Please notice, choice 4 is negative 64 x to the 5th, which is what you would get if you added those two exponents. Remember again, x squared cubed is x squared times x squared times x squared. There are actually 6 x's multiplying each other there, right? Make sense of that exponent. All right, let's take a look at number 15. Which function has the smallest y-intercept? All right, well, one thing you should absolutely positively know about the y-intercept of any function, doesn't matter what function we're talking about, the y-intercept of any function occurs when x equals 0, right? It's the y value when x equals 0. And that's the key, because you can always figure it out. Like for choice 1, if I figure out what g of 0 is, that's 2 times 0 minus 6. That's 0 minus 6, and that's negative 6. So that's its y-intercept. Its y-intercept is negative 6. Here, f of 0 would be the square root of 0 minus 2. The square root of 0 is 0, and 0 minus 2 is negative 2. So here, the y-intercept would be negative 2. Here, we've got a table, right? And we can't really plug 0 into the formula this time, but we can just look for it right in the table. And the y-intercept here happens to be y equals 1, right? When x was 0, y was equal to 1. And finally, in this graph here, we can literally just read it off. That's the point 0 comma negative 2. So the y-intercept here is negative 2. All right, so we're trying to figure out the choice that has the smallest y-intercept, which they had said the least y-intercept, but whatever. Technically, it's negative 6, right? Negative 6 is less than negative 2, less than negative 2, and obviously less than 1. So the one that's got the least y-intercept is choice 1, g of x equals 2x minus 6. Now, if you just know that with a linear function, this is the y-intercept, well, good for you. You know, you just got to watch out, because it's not always the number at the end. In fact, if I had something like this parabola here, right, the y-intercept is not positive 5. I mean, it could be, but only if k is equal to 0. The point is, it's not always the number that's just sitting at the end. Many times it is, but not always. It is the number when x is equal to 0. Let's talk about number 16. Which domain would be the most appropriate to use for a function that compares the number of emails sent, x, to the amount of data used for a cell phone plan, y? All right, there's a lot to unpack here, not the least of which is simply what the term domain means, okay? Remember, you got these functions, and they're taking numbers over here, and they're changing them into other numbers over here. The domain, those are the inputs or the x values. Now, this is a function that has context to it. So what does this function do, right? It compares the number of emails sent, x, right? So the input is the number of emails sent to the amount of data for a cell phone plan, y. All right. Now, what kind of numbers could we put in for the numbers of emails sent? Well, I could send 0 emails, right? I could send 0 emails. I could send 1 email. I could send 2 emails, 3 emails, 4 emails, etc. All right, by the way, emails for you kids out there that are watching this and you only use things like texting and stuff like that. Emails are kind of like letters. And letters are kind of like texts, but written on paper, and you sign your name and stuff. Anyway, never mind. So the point is, the inputs could be numbers like 0, 1, 2, 3, 4, etc. So what are those? Are they integers? Well, they are, except the integers are whole numbers that include both positive and negative. So no, not negatives. Are they whole numbers? Yes, that's what we have, right? Now, I don't want to say rational numbers because rational numbers are all of these, but they also include things like fractions, 1/2, 3/4, 7/3, 1.8. They also include negative fractions and negative integers, all right? And irrational numbers, definitely not, right? You can't send pi number of emails, okay? That would be like an irrational number. So it's definitely the whole numbers that would represent the domain of this particular function. All right, number 17, quickest problem on here. Eric deposits $500 in a bank account that pays 3.5% interest compounded yearly. Which type of function should he use to determine how much money he will have in the account at the end of 10 years? All right, so here's the key. You're supposed to know that when you're dealing with interest rate that is compounded, that is an exponential function. More than that, I could even give you the exponential function. The exponential function is y equals 500 times 1.035 raised to the t, where t is the number of years. Now, if I wanted to know how much money I had after 10 years, I would just put 10 in there, right? I'm not sure if I have a function anymore as much as an expression, but whatever, right? This is an exponential function because you're multiplying to get the next value each time, right? It's a multiplicative process, which is an exponential process. Not linear, not quadratic, certainly not absolute value. Okay, number 18. This is a bit of an ugly problem, but let's walk through it. Given the sequence 4, 7, 10, 13. When using the arithmetic sequence formula, a sub n equals a sub 1 plus the quantity n minus 1 times d to determine the 10th term, which variable would be replaced with the number 3? Wow, okay. So this is one of those formulas that's on the formula sheet way back at the back of your test, okay? And you could look it up, but it's sitting right there, so don't. Right? So what are all of these things? Well, this formula is used to predict a particular term in an arithmetic sequence. And what an arithmetic sequence is one, right, where the amount that you add or subtract to get to the next term is always the same. So in this particular sequence, I'm adding 3 to keep getting to the next term. That's what's called the constant difference. And that shows up right here. Right? So the constant difference, what you add on each time to get to the next term, right, is equal to 3. A sub 1, that's simply your first term. That would be the number 4. N, that's how many terms you have, right? So that would be whatever. If I'm looking for the, well, in this case, if I was looking for the 10th term, n would be equal to 10. D would n would certainly not be equal to 3. Okay. So now, moving from a sequence all the way to stat, let's take a look at number 19. Below are two representations of data. Data set A is just a data set, and of course B is a box plot. Then it says which statement about A and B is true. 1, the median of A is greater than the median of B. 2, the range of A is less than the range of B. 3, the upper quartile of A is less than the upper quartile of B. 4, the lower quartile of A is greater than the lower quartile of B. Oh my. Okay, so basically what I have to do for these two data sets is I have to be able to figure out what their medians are, their ranges, their upper quartiles, and their lower quartiles. Remember, the upper quartile is also known as the third quartile. The lower quartile is also known as the first quartile. So let's first just talk about the medians. Now, in data set A, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. I love it because that means I can just go to the 5th one, which is right here, and that's my median. Okay, so my median is equal to 6. Let's find our median here. That's going to be the line right in the middle of the box. This median is also 6. So that first statement that says the median of A is greater than the median of B is not true because the medians are, in fact, equal. All right, let's figure out the ranges. Now remember, the range is simply the greatest value minus the least values for the range, right? The range for A is going to be equal to 9 minus 2, which is equal to 7. And the range for B, right, is going to be 10 minus 4, which is equal to 6. So number 2 says the range of A is less than the range of B. Well, the range of A is 7, the range of B is 6, so that is also a false statement. All right, upper quartiles. Now, on the box plot, the upper quartile is going to be very easy, so let me just take care of that one really quick. Q3 here is going to be equal to 9. Now, the upper quartile on the one up above, that one's a little bit trickier. Now remember, what I have to do to calculate the upper quartile when I've got like a list of data is I'm going to eliminate the median, okay? I'm going to look at the upper half of the data and I'm going to find its median. Now, in that case, what I have to do is I actually have to find the average of 7 plus 8, that's pretty easy, which is 7.5. All right, so let's take a look to see if that choice is correct. The upper quartile of A is less than the upper quartile of B. The upper quartile of A is 7.5. The upper quartile of B is 9. That looks like our winner. Whew, man, I hate those ones where I have to go pretty much down through all of them, and I'm glad it just wasn't choice 4. Could have been choice 1. I would have been done with this problem very quickly, but it wasn't. All right, let's take a look at problem number 20. Oh man, which system has the same solution as the system below? All right, I hate these problems. All right, so the point of these problems, and you're like, you wrote the book. I know, but it's not my choice. All right, so here's the thing, right? I bet I could give, 95% of you this thing and say, solve this system, right? And you remember how you solve it. You solve it by like maybe multiplying this first equation by 2 and then adding it to the second equation and having the positive 2x and the negative 2x cancel out, and then you solve for y and you take your y variable and you put it back into one of the two equations and you get x, and you all know how to do that, right? So what is this problem about, right? Well, this problem is about what you're allowed to do with a system of equations in terms of manipulating it. And here's the rub of it, right? In these problems, what they've typically done is they've taken one equation and they've multiplied it by something on both sides. And that's completely fair game. So for instance, if we look at choice 1, the first equation, negative x plus y equals 6. I kind of look at these two and I go, I don't know where that came from. But 2x plus 6y equals 20. That comes from just multiplying that first equation by 2 on both sides. So that's like a legitimate equation. The question is, where did this one come from? Well, besides multiplying both sides of the equation by some number, you can also add the two equations or subtract them. So just for a minute, let me add these two together and see what happens. When I add those two equations together, x plus negative 2x is negative x. When I add 3y plus negative 2y, I get positive y. And when I do 10 plus 4, I get 14. Right? So when I add these two equations together, I get a perfectly legitimate equation that has the same solutions as this system does. Now, negative x plus y is equal to 6, and negative x plus y equals 14. Those are incompatible. They can't be both equal to 14 and equal to 6 at the same time, so that one's not correct. Now, if I look at choice 2, though, I see that negative x plus y equals 14. And I see that 2x plus 6y equals 10, remember this, or 20. Remember, this one just comes from doubling this one, and so that's it. That's the one that will have the same solution as this system. The idea is, right, if you get a problem like this, first thing you want to do is say, well, okay, when I look at any given choice, can an equation be produced from one of these two by just multiplying both sides by some number? It could be a positive, and it could be a negative number that they multiply by, but that should be pretty obvious. Then the second question is, if I just add the two equations together, what happens? What do I get? And typically it's just adding them. You could also subtract them. It's less likely that they're going to make you think that way, but that's what's going on in this problem. Kind of drives me nuts because it really doesn't have anything to do particularly with solving them. Okay, let's take a look at 21. Given the pattern below, which recursive formula represents the number of triangles in this sequence? Okay, now this gets into a piece of terminology called a recursive formula. So sequences, right, are these lists of numbers, 2, 3, 8, 20, whatever, right? That's a sequence of numbers, all right? Sometimes they're just given with formulas like this. Other times, though, what happens is we're given their first value and then given some formula that tells us how to calculate any value if we know the one before it. So for instance, this particular formula says, well, the first value should be 2, and then any given value should be the previous value plus 3. This one says the first value should be 3, and any given value is the previous value plus 2. Right? And that's what a recursive type of formula is, where they give you the first value or maybe the first couple values, and then they tell you how any given value depends on ones that came before it. These aren't even recursive formulas. So even if one of them did properly predict the number of triangles, and they don't, but even if they did, they wouldn't be the right answer because they aren't a recursive formula. So it's one of these two, and it's really easy given that the first pattern, A1, has 3 triangles. It's got 3, so it's got to be this one, right? It's got to be choice 4. And in fact, what's happening, right, is you take these 3 and you add another 2. Then you take these 5 and you add another 2. Then you take these 7 and you add another 2. So this formula that says, well, start with 3 and then figure out the next one by always taking the previous one and adding 2 to it is the correct recursive formula. All right, let's take a look at problem 22, which is all about terminology. Students were asked to write an expression which had a leading coefficient of 3 and a constant term of -4. Which response is correct? All right, now you really got to watch out for this one, okay? This is really a pretty simple problem, but it's all about this terminology, leading coefficient of 3 and constant term of 4, right? The leading coefficient is not the first number you see. It is the coefficient or the number that multiplies the variable that has the highest power. In other words, if you put a polynomial in what is known as standard form, that's having the highest power written first, then the next highest power, the next highest power, etc., right, the leading coefficient would be the first number. But better than that, the leading coefficient is the coefficient, the number that multiplies the highest power. So if you look at choice 1, right, the highest power is x to the third, and the number multiplying it is -2. So that's not right. Choice 2, the highest power is x to the fifth, and the number multiplying it is -3. Still not right. Choice 3, the highest power is x cubed, and the number multiplying it is 3. Ah, that's good. So this one could be it. Then when I look at choice 4, the highest power is x to the fourth, and its coefficient is also +3. So this could be right. All right, so let's talk about the constant term of -4. The constant term is the term that's added on that doesn't involve a variable at all, right? It's the +7 at the end or the -2 at the end, right, when written in standard form. So when I take a look at number 3, its constant term is +4. And when I look at choice 4, its constant term is -4, right? So our winner is choice 4. All right, let's keep going. 23. Sarah travels on her bicycle at a speed of 22.7 miles per hour. What is Sarah's approximate speed in kilometers per minute? All right, fantastic. This is really a unit conversion problem, okay? So let's take a look at how these are done. I'm going to write that rate 22, actually let me give myself a little bit more here. 22 miles per hour. And at the end, I want something that's in kilometers per minute. So ultimately, I need to cancel the miles and get kilometers, and I need to cancel the hours and get minutes. Now, one of those conversions you should know immediately, which is the fact that 1 hour is equal to 60 minutes. Now notice, right, the hour is in the numerator to cancel the hour in this denominator and leave me with minutes in the denominator, which is where I need them. But now I need to somehow convert miles into kilometers. For that, I don't know that conversion factor, so I go all the way to the end of the test, where they have all of these nearly useless conversion factors for this and any other math test you'll ever take at the high school level. It's true. But what I like is I see right here 1 mile is equal to 1.609 kilometers. 1 mile is equal to 1.609 kilometers. I'm going to try to keep that in my head. 1 mile is equal to 1.609. Oh, there we are. There we are. All right, so times 1 mile, 1.609 kilometers. I'm going to have my miles cancel, right? And those are going to leave me with kilometers in the numerator. So let's do it. All right, let me pop over to my calculator. I'm going to go to dock and just clear out my screen real quick. Minimize this. I've got 22. Let me bring this way up here to make sure you can see it. All right, that's a little bit better. And of course, nope. Why is that not staying in front? That's weird. View. Okay. I don't know. Anyway, used to stay in front for me. We've got 22, right, divided by 60, but then times 1.609. Anything in the numerator multiplies, anything in the denominator divides, and I get 0.58999, etc. Now it stayed in front, 58996, etc. Jeez. Anyway, so yeah, there it is, 0.58996, etc., which is just about 0.6 kilometers per minute. It'd be so fantastic if, you know, you probably all have a sense for how fast 22.7 miles per hour is. You know, you're old enough, you've been in a car enough, you have a sense for that, right? And hopefully you also have a sense that a kilometer and a mile aren't that different, right? 1 mile, 1.609 kilometers. So to be going 36.6 kilometers per minute, you'd be like, pew! I don't know how that compares to the speed of sound, all right? But it's probably pretty close to it. All right, let's take a look at problem 24, and then we'll get past the physics. All right, which ordered pair does not fall on the line formed by the other three? This is, I first saw this problem and I was like, oh my goodness, what in the world? So the idea is they gave you 3 points, 3 of them fall on a line, and the last one doesn't, and which one doesn't? Now, one way to do this is definitely with slopes, right? So all points on a line, when you calculate the slope between those 2 points, will give you the same number, okay? So one way to do it is just to start calculating a bunch of slopes. And then I thought to myself, I'm gonna make a scatter plot. I'm just gonna simply look at a picture and see which one of the three, or which one of the 4 doesn't fall in line with the other 3. So let's bring out the TI Inspire yet again, all right? And let's see, I'm gonna go to dock, actually menu, nope. I can't do an insert, that's weird. Okay, I'm gonna go back here. All right, this is the first time I'm gonna put a little data in. Okay, I'm gonna put in 16 for X and 18 for Y. I'm gonna put that point in. I'm gonna put 12 in for X and I'm gonna put 12 in for Y. It's gonna be that point. I'm going to put in 9 for X. This is probably the very slow way to do it. And I'm gonna put 10 in for Y. And then I've got 3 comma 6. So I'm gonna put 3 in for X, oops. And I'm gonna put 6 in for Y. So I'm putting these data points in. Now what I'm gonna actually do, I'm gonna call this X. I'm gonna call this Y, okay? So all I've done, let me just be very clear about this. I just took all these points and I put all the X values in column A. I put all the Y values in column B as if I was gonna do a scatter plot, do a line of best fit, stuff like that. I'm not gonna do that, but I am gonna do the scatter plot. I'm gonna do that now by hitting menu, or actually by going to dock and going to insert data and statistics. Now when I do that, I get this, which is confusing. So I'm gonna go click to add a variable. I'm gonna put X there. Click to add a variable, I'm gonna put Y there. And there it is, right? These 3 fall on a beautifully straight line, even if I can't draw it. But this last one at 16, 18 simply doesn't. Now again, what you can do is you can find the slope between these two, and find the slope between these two, and find the slope between these two, and then find the slope between this one and these guys. And you'll find that the slopes between these three are always the same number, but as soon as you get this one involved, you get different numbers, and that means that doesn't lie on the line. But boy, doesn't it make sense to just do that scatter plot and be like, there it is. That's the one that doesn't quite fit. So, 16, 18. All right. That looked like it was like at 18, 16. No, it's at 16, 18. Okay. Thought maybe I had switched them around. And that concludes our multiple choice section. So let me just take a moment, break, have a little bit of lemonade. It's a little bit past 7. We've been going for an hour. So you all have the Algebra 1 Regents exam tomorrow morning. In theory, it should start around 8 o'clock. Last for 3 hours. And if you have extended time, maybe even 4.5 to 6 hours, right? Lots of time on this exam. Tons of time to work, check over your problems, go with multiple approaches, algebraic approach, graphical approach, all that kind of stuff, right? And by 11 o'clock tomorrow, you're not going to think about math for the rest of the summer. Now that sounds like a horrible summer to me, okay? But I'm sure for many of you, that'll be awfully nice. One thing I wanted to mention in all of my reviews is that you should have Monday off, right? Monday is Juneteenth, or it's Juneteenth celebrated. Actually, Juneteenth is Sunday. Sunday the 19th, June 19th. And if you didn't know about it, this is a new federal holiday, right? And it celebrates the, if you will, kind of the ending of slavery in the United States. Now, you could have like a lot of different views on, you know, all sorts of things in our country right now in terms of politics and social justice issues and things like that, all right? But at the end of the day, I hope that what we can all agree on is that the end of slavery in this country is something that should be celebrated. On June 19th, 1865, a Union general in Galveston, Texas, read a proclamation that freed the last slaves in this country. That's actually not entirely true. It actually happened 2 months later in like many months later in December, but it's celebrated marking that event. So I wish you all on Sunday a happy Juneteenth, and hopefully all of you on Monday will take a little bit of time on that day off to sort of reflect on it. All right, I think I need some more lemonade. It's coming, it's coming. There it is. Oh, yes. That was awesome. I love green screens. I know, I got the lemonade down there, but. Oh, yeah. Oh, geez, God, man, it's concentrated sugar there at the bottom. All right. Thank you, magical lemonade container. Hey, it's not like we have a Spielberg budget or anything. All right, so I say we get back now to Algebra 1. All right, so anyway, part 2 in Algebra 1 are free response problems that are worth 2 points each, all right? So you've got to answer all of these things. There's 8 of these 2-point questions, and these are dicey. You got to watch out. Any mistake on these, even if you've done like almost all the work right, and you're going to lose 1 out of 2 points, which is a real shame. Anyway, let's jump in and do an inequality where they have given us far too much room. Let's take a look at 25. Solve algebraically for y. 4 times the quantity, y minus 3, is less than or equal to 4 times the quantity, 2y plus 1. I love the fact that they put random 4s there for no reason. We could cancel them out of both sides and the problem would just work out the way it should. But anyway, I'm not going to do that. I'm going to do it the way most of you probably would, which is to distribute the 4 on the left-hand side and distribute the 4 on the right-hand side, in which case we have something that looks like 4y minus 12 is less than or equal to 8y plus 4. All right, great. All right, now, again, all depends on how you want to do it. Do you like getting your y's on the left side, on the right side? I'm going to actually bring all my y's over to the left side and move all my numbers over to the right-hand side, just so that I can remind you of a particular thing that is true about inequalities, but let me just subtract an 8y from both sides. 4y minus 8y is negative 4y, minus 12 is less than or equal to positive 4. I'm now going to add a 12 to both sides, and I'm going to get negative 4y is less than or equal to 16. And here's the real whammy. Now I'm going to divide by negative 4 on both sides. But as soon as I do that, I'm going to flip the inequality symbol, right? When you either divide both sides of an inequality by a negative or multiply both sides of an inequality by a negative, but honestly it's mostly the division thing, then you switch the direction of the inequality. So dividing by negative 4 on both sides gives me y is greater than or equal to negative 4. And that's it. Now you can imagine, right? You're working through all of this, you forget to flip the inequality sign, you are definitely going to lose a point. You may even lose 2 points for that, because that's really a big thing in terms of inequality solving. So watch yourself. That thing's an entire page. All right, let's do a graph. Let's take a look at 26. Graph the function f of x equals the absolute value of 1/2 x plus 3 over the interval negative 8 is less than or equal to x is less than or equal to 0. Awesome, right? We're just kind of graphing a function. We're going to put it into our graphing calculator. We're going to get a table of values, and we're just going to use that table of values to graph. Now, again, remember, this is worth a whopping 2 points. And if you don't pay attention to this interval, you're going to lose one of those 2 points. Make sure that the graph goes from x equals negative 8 to x equals 0, and there's nothing outside of that, okay? So let's do it. All right, I'm going to go to Doc. I'm just going to open up a brand new document, I'm going to erase all this stuff. No, I don't want to save. I'm going to add a graph. Here we go. I need to put in my absolute value symbol. That is totally not what I wanted to do. Here we go. And I'm right on the absolute value. And I need the absolute value of 1/2 x plus 3. I need to make sure that plus 3 is in the absolute value. Now here I'm like, I need to make sure it's in the absolute value bars, and then it didn't get there. Oh, come on. Stop. Okay. That's right. When all else fails, just start again. What happened there? All right. One more time. 1/2 x plus 3. Enter. There it is. Okay, great. Now, it's all nice and good that I've put the function in, right? And that I have a nice little graph of it. But a couple things, right? I really only want this graph from negative 8 up to 0, so this is too big of a graph, and I've got to get the exact values. So I'm going to go into my table by hitting Menu, Table, and I want a split screen table. Now, again, keep in mind, right, I'm just going from negative 8 to 0, right? So I want to just start writing down these coordinate points like negative 8, comma 1. I don't even need to have this one, right? Negative 6, comma 0, negative 4, comma 1. So let's do that. Let's minimize this. I'm going to actually do handheld only for a minute. I know that's awfully small and you can't see it. I apologize. I've just got to use it in order to create this table of values. So when x was negative 8, there we go, y was 1. When x was negative 6, y was 0. When x is negative 4, y is 1. When x is negative 2, y is equal to 2. And when x is 0, y is equal to 3. All right, I'm going to go back to both of them, minimize. There we go. There's my table of values. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 1. Negative 6, 0. Negative 4, 1. Negative 2. Did I count wrong? I think I did. Negative 2, 2. I counted wrong. Got to get rid of these. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 1. There it is. All right, that's a little bit better. Those are my points. And that That is it. You know, just because they gave you a giant piece of graph paper doesn't mean you're going to hardly use any of it. This is the whole thing. That's it. 2 points. Now again, one of the things that's a shame is as soon as you do this, as soon as you do that, you've lost a point. As soon as you've done it, you've lost a point, right? They only want this interval, and you've got to pay attention to that. So we get rid of that, and we stop it right there. All right, let's keep going. They give you a lot of space on here. You hardly ever have an issue with space. Let's take a look at number 27. The table below shows the height in feet, h of t, of a hot air balloon and the number of minutes t the balloon is in the air, right? So we've got this table, time, minutes, 2 minutes, 5 minutes, 7 minutes, 10 minutes, 12 minutes. At 2 minutes, the balloon is 64 feet above the surface. At 5 minutes, it's 168 feet above the surface, etc. And that'll be the last time we'll ever look at that table, because then it goes on to say the function h of t equals 30.5t plus 8.7 can be used to model this data table. Explain the meaning of the slope in the context of the problem. All right, so what they've done is they've taken this data and they've modeled it using this linear function. And let me write it so that you can see it a little bit better, but I'm going to write it in terms of y equals mx plus b, right? So when they say explain the meaning of the slope in the context of the problem, the first thing I have to do is be like, well, there's the slope, right? And what is the slope? The slope is always the change in this divided by the change in that. It is the feet per minute. So in other words, what are we talking about? A hot air balloon? That hot air balloon is rising at a rate of 30.5 feet per minute, right? It's the change in y over the change in x. In this case, that's the change in height divided by the change in time. That's feet per minute. I think I may have said just feet per second. I apologize. So the balloon is rising at a rate of 30.5 feet per, and again, watch your units, minute, feet per minute, right? Slope is always a rate, and the units can be figured out by looking at the units of the y per unit of x. All right. Second part of this problem, remember this is a 2-point problem, 1 point, 2 point, right? Explain the meaning of the y-intercept in the context of this problem. Well, again, in y equals mx plus b, this is the y-intercept. Now the y-intercept is, whoa, man, everything just got blurry on me for a second. The y, it's all good, it's good now. I think it was my eyes. The y-intercept is the output when the input is 0. So in other words, when t is equal to 0, the height of the balloon is 8.7 feet. In other words, the balloon starts at a height of 8.7 feet. And that's it. Right? The slope in a linear function, the number that's multiplying x or t or whatever, that is a rate. How fast the y is changing per unit of x. The y-intercept is what the initial y value is when the x value is 0. All right, let's keep going. Whoa, moving. Ah, finally a free response factoring problem. 28. Factor x to the fourth minus 16 completely. All right, wow. There's so much I want to talk to you about with factoring, but it's not really the time or a place for that. So let me give you the abridged version, right? Factoring is breaking a polynomial down into the product of a bunch of other polynomials, okay? Just like breaking the number 12 into 3 times 4 is factoring, breaking this into something times something, maybe times something is also factoring. Factoring completely means you've done it until you can't factor anymore, Now there's three types of factoring that you've learned in this course and in previous courses, right? One type is GCF, all right? That's when I can factor something out of both of these two terms, but I can't. There's nothing there to be factored out. There could have been, but there wasn't in this particular problem. The second type of factoring is trinomial. That's when you have three terms and you break it into a binomial times a binomial. We saw that in that one multiple choice problem. And then there's the difference of perfect squares. Now remember what that looks like. That looks like something like this. X squared minus a squared is equal to x minus a times x plus a, or x plus a times x minus a. It doesn't matter. It's multiplication. It's commutative. Now that's the way this fits, because x to the fourth is x squared squared, and 16 is 4. Whoops, that doesn't look like the number 4. That looks like the number gibberish. Let's see, there we go. 4 squared. So x to the fourth minus 16 can be written as x squared minus 4 times x squared plus 4. Now, oftentimes when we factor an expression, we do that and we're done. If I had x squared minus 100 and I wrote it into x plus 10, x minus 10, that would be done, right? But here, x squared minus 4 is also the difference of perfect squares, and it can be factored as x minus 2 times x plus 2. Now, of course, a natural question would be, well, then why not factor x squared plus 4, right? Why not factor that? And the answer is because you can't. At least not right now, right? You can't right now. There is nothing right now that you know of that you can do to factor that. It's not x plus 2 times x plus 2, and it's not x minus 2 times x minus 2. Neither one of those, when multiplied together, gives you x squared plus 4. In fact, the sum of perfect squares in general cannot be factored with real numbers. All right? So this is as factored as it's going to get. In fact, it is factored completely. Doop-a-doop-a-doo, ba-doop-a-doo. All right, let's take a look at a question that involves Mike. Mike knows that 3, 6.5 and 4, 17.55 are points on the graph of an exponential function g of x, and he wants to find another point on the graph of this function. We doing okay, Joey? Yeah. Okay, just checking. You never know. We're going on an hour and a half now, so things are going to start to fall apart. Anyway, so Mike's got these 2 points on an exponential function, and he wants to find another point on the function. So here's how he's going to do it. He's going to subtract 6.5 from 17.55 to get 11.05. Next, he's going to add 11.05 to 17.55 to get 28.6, and he states that 5, 28.6 is a point on g of x. Is he correct? Explain your reasoning. Oh, Mike. No, Mike. No, Mike. No. Jeez. Exponential function, Mike, not linear, not linear. See, what Mike is doing is he's actually coming up with the next point that would be on a linear function, right? Linear functions are all about finding this difference and adding it on. I mean, think about this for a second, right? And we could actually put this on our graphing calculator. But right, he's got this point at like 3, 6.5. And then he's got this point at 4, 17.55. So what does he do? Right, he takes these two y values and he subtracts them, right, which finds that vertical distance, right? And then you got this horizontal distance, which is 1. And then he goes over and he just adds that on again to get the point 5, 28.6, right? He just takes that difference and he adds it on. And so what he's doing is he's getting a linear function. No, this would be for a linear function. In fact, and we don't have to write this down because they didn't ask us what the correct way was. They just asked, was this correct? And the answer is no, it's not correct, right? But the correct way would have been to actually take 17.55 and divide it by 6.5, come up with that multiplying factor, and then multiply 17.55 by whatever that number was to get the next number. So exponential is all about multiplying by the same number to get to the next number. Linear is all about adding the same number. So as soon as Mike subtracted, and he subtracted to figure out how much he had to add on to get to the next one, right? And as soon as he added that on, it's not exponential, it's linear. Ooh, number 30. Use the method of completing the square to determine the vertex of f of x equals x squared minus 14x minus 15. State the coordinates of the vertex. All right, so now you probably know multiple ways of finding the vertex, also known as the turning point, of a quadratic function, also known as a parabola. Lots of also known as, sorry. But this problem is very specific. They want us to complete the square in order to find it. Now, it wouldn't hurt to actually just take, one of those other methods, maybe put this in your calculator, look at a table of values, do something like that to figure out what the vertex is at. But let's see how we do it by completing the square. Now, the first thing I'm going to do is I'm going to actually take this, I'm going to take this f of x, I'm just going to replace it with a y. I just find it easier to work with. And then I'm going to get rid of this little stray red mark. So x squared minus 14x minus 15. Great. All right. So I've got x squared minus 14x minus 15. We're all set. Let's talk about completing the square. So the way we complete the square, as long as the leading coefficient is equal to 1, and it is, the leading coefficient on the x squared is equal to 1, and it is, what we do is we take this linear term, this linear coefficient, negative 14, and we divide it by 2, and we get negative 7. And then we take negative 7 and we square it, and we get 49. Now, what do I do with that 49? Well, what I'm going to do is I'm going to do x squared minus 14x plus 49. I'm going to add that 49 to the first two terms. Now, I can't just add a 49, but I can add a 0. So I'm going to add a 49 and subtract a 49 at the same time. Now, I know that's a little like, it's almost like a magician's sleight of hand, right? What I'm really just doing is adding 0 to both sides. Now, some of your teachers probably said, well, add 49 to this side and then add it to the left-hand side as well. Great, that's awesome. That's sort of like keeping the scales balanced. For me, I just like to add 49 and subtract it right away. Now, when I do that, what happens is this trinomial now is a perfect square that can be factored as x minus 7 times x minus 7. These can combine into negative 64. Now, finally, I'm going to rewrite that, whoops, I'm going to rewrite that as x minus 7 quantity squared minus 64. All right, I've got it. I now have this parabola in what is known as vertex form, the vertex form of a parabola. And we saw this before in that problem on parent functions. Remember the one that had like y equals x minus k squared plus 5? Okay, here we have y equals x minus 7 squared minus 64, which means we've taken this thing that has a vertex at 0, 0, and we've shifted it 7 units to the right and 64 units down, so the vertex now is at the point 7, negative 64. And that is how you use completing the square to find the vertex. Oh, here we go. Oh no, that's not what we want. Come on. Oh, stop. Well, I don't want that. There you go. Nice and easy, nice and easy. I feel like I skipped a problem there. Nope, I didn't. Celsius and Fahrenheit. If you ever find yourself in Europe or someplace like that, this might help. Actually, anywhere outside of the United States. Problem number 31. The temperature inside a cooling unit is measured in degrees Celsius. Josh wants to find out how cold it is in degrees Fahrenheit. Solve the formula C equals 5/9 times the quantity F minus 32 for F so that Josh can convert Celsius to Fahrenheit. All right, so this is one of these problems, right, where we've got multiple variables in a particular formula, and we want to solve it for one of the variables. Now, specifically, we want to get f all by itself. Now, I know the tendency is to want to distribute that 5/9 through the parentheses. And quite frankly, if 32 times 5/9 was a nice number, I would totally do it. But 9 doesn't divide nicely into 32, so I'm not going there. Okay, in fact, what I'm going to do is I'm going to start to get f by itself, all right, by simply undoing the order of operations. F had 32 subtracted from it, then multiplied by 5/9. So the first thing I'm going to do is multiply both sides of this equation by 9/5. All right, that leaves me with 9/5 times c on the left side, and f minus 32 on the right side. Now, of course, it's very easy to solve for f by just adding 32 to both sides. And I'll get f all by itself on the right-hand side, granted. And I'll get 9/5 c plus 32 on the left-hand side. You can most certainly distribute the 9/5 through and then solve for f. You can do that. At some point, you're going to have to multiply both sides by 9/5 or divide both sides by 5/9. Those two things are the same. But somehow, you'll get down to this formula. Oop, oop, boom. Ah, man. Every time. Well, maybe not every time, just recently. All right, here we go. Problem number 32. Remember, we're still on 2 pointers. Problem number 32. Solve 4w squared plus 12w minus 44 equals 0 algebraically for w to the nearest hundredth. Man, I cannot believe this is a 2-point problem, okay? Now, to begin with, it's a w squared. So that means there's going to be 2 solutions. How many solutions? 2 solutions. How many? 2. Why? Because the exponent's 2. All right, the number of solutions almost always corresponds to the highest power. Almost always. You'll learn more about that in Algebra 2. Anyway, I want to solve this for w to the nearest hundredth, which means they're going to be messy answers, which means we're not likely to get them by factoring, but we're going to get them by using the quadratic formula. That's right. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. This formula is at the back of the test in your formula sheet. I know the variable here is w and the variable here is x, but it doesn't matter. Now, you can make your life exceptionally easier in this problem, much easier, if you notice that you've got a 4w squared, a 12w, and a 44 and a 0. And all 4 of those numbers, all 4 numbers, 4, 12, 44, and 0, are all divisible by the number 4. So, to make my life much easier, I'm going to divide both sides by 4. Now I have to distribute the division, right? I get 4w squared divided by 4 plus 12w divided by 4, whoops, minus 44 divided by 4 equals 0 divided by 4. Now you might say, this isn't making it easier, this is just making it longer. But I'm thinking this equation is going to be much easier to solve with the quadratic formula, right, than the original one. You could also solve this one graphically. You could, if you really loved fractions, also solve it using the method of completing the square. I'm not going to do that. I'm going to use the quadratic formula. So here we go. Let's do it. Quadratic formula. W equals negative b plus or minus the square root of b squared minus 4 times a, that's the leading coefficient, times c, all divided by 2 times a. Now, I always advise students when they're using the quadratic formula to figure out the number underneath the square root independent of everything else. So I'm going to bring my calculator back out real quick. All right, I need to figure out what 3 squared minus 4 times 1 times negative 11 is. All right, so I've got 3 squared minus 4 times 1, whoops, times negative 11. All right, that is simply the number under the square root. All right, the number under that square root is going to be 53. I'm going to put this back away for the time being. All right. So that's negative 3 plus or minus the square root of 53 over 2. Now, many of you are used to, at this point, simplifying the square root, dividing by the 2, doing all of that. You don't need to do any of that. Number one, the square root of 53 can't be simplified. 53 is a prime number, I'm pretty sure. Anyway, even if the square root of 53 could be simplified, even if you could, you wouldn't want to do it. All right, it's a calculator problem, right? It says, get my answers to the nearest hundredth, right? That's what I'm going to do. So, negative 3 plus or minus the square root of 53 over 2. Let's do it. I've got, actually, I'm going to use the fraction bar since there's a fraction in this formula. Negative 3 plus the square root of 53 all over 2. Now, I got to do these each one at a time. That's going to be 2.14. That's one of them. And the great thing about these calculators is now I'm just going to hit the up arrow twice, highlight that expression. I'm going to go back, use the back button, the delete, put a subtraction. Watch out that you don't put a negative symbol. Enter, and I get negative 5.14. And those are my two solutions to the nearest hundredth. Again, one could also solve this problem graphically. The way that you would do that is by putting in y equals and putting this in terms of x, graphing it using the 0 command to figure out where it was equal to 0. But then you'd have to produce the graph and do a bunch of things like that. And I like the quadratic formula. It works. It works. All right. Oh, finally. Part 3. Yes. All right. Let's talk a little bit about part 3 questions. And let me get a little drink. My voice is starting to go. Just what you wanted to hear. Me drinking lemonade. Oh, man. Whew. And after this, I only have to do the Geometry and Algebra 2 reviews. Thankfully, those are Monday night. That's Geometry. And Tuesday night, that's Algebra 2. If you're planning to join for all three, I wonder what math class you're taking or exactly why you're not watching better television. But, hey, join for all three. Who knows? Let's talk a little bit about part 3 questions. So these are going to be longer ones, right? There's going to be 4 of them. Each one of them is going to receive 4 credits. So they're going to be 4 points a question. They're going to be more involved. Honestly, most of the time, they're kind of 2 two-pointers. That's what they are. Each one of them is 2 two-pointers. Hey, problem number 33. Joey recorded his heart rate in beats per minute. Hey, Joey. After doing different numbers of jumping jacks, I feel like we should get you on camera to illustrate. His results are shown in the table below. Number of jumping jacks is X and the heart rate is Y, right? In beats per minute. How many? Oh, I'm sorry. Yes, that was loud. My apologies to everyone watching YouTube. Instagram people are like, who cares? All right, so anyway, when Joey did 0 jumping jacks, his heart rate was a robust 68 beats per minute. After 10 jumping jacks, 84 beats per minute, 15 jumping jacks, 104 beats per minute, etc. You probably already know where this problem is going. The first part of the problem says, state the linear regression equation that estimates the heart rate per number of jumping jacks. All right, so in other words, I need to use the linear regression on a calculator to come up with the line of best fit. Let's do it. All right, I'm going to open up a brand new document. New document. I am going to go into my listen spreadsheet. I've got to put this in. In order to put this data in, I'm going to have to make the calculator seriously small. I apologize for that, but here we go. I'm going to put 0, 10, 15, 20, and 30. Again, my apologies for how small this is. And then I'm going to have 68, 84, 104. Yeah, that's 104, 100. I love the fact that your heart rate went down when you did 20 versus 15, Joey. That's weird. It's very weird. Okay, all right. So now I've got the data in, and I, for some reason, did that. Let me go back to this view and make it larger. All right, great. I got all my data in, right? And again, this is very calculator specific. If you're doing this on the Casio or on the TI-83, it's a different method, but still, the idea is the same. I'm going to go into menu, I'm going to go into statistics, I'm going to go into stat calculations, and I want linear regression mx plus b. My X list. Oh, I should have named these. Can I cancel? Yes, I can. Can I escape? Can I escape? Nope, here we go. Give me a moment. This was jumping jacks. So I'm gonna put in JJ. Whoops. Come on. Here we go. Jumping jacks. And B was heart rate. So I'm gonna put HR for heart rate. It's very, very, very good when you're doing these types of problems to give a label to your data, okay? Now let's do it. All right, menu, statistics, stat calculations, linear regression. X list was jumping jacks, Y list was heart rate. Everything else looks pretty good. I'm gonna hit OK, and here we go. So my regression equation is mx plus b, my m is 1.72, my b is 69.4. How they made these come out so nicely is beyond me. All right, and later on we'll need some things down here. But these two things I need, right? Y equals mx plus b, m is 1.72, b is 69.4. Let me get those two down. Let me just move this up. Why? That's so weird. Y equals 1.72x plus 69.4. All right, let's take a look at the next part. State the correlation coefficient of the linear regression equation rounded to the nearest hundredth. Okay, so the correlation coefficient is this thing that we call the R value, and it measures how well a line of best fit or other type of curve would fit the data. And here it is on our calculator. Let me just increase this size. It's right down here. Notice they have an R squared value, which is literally this R value after it's been squared. Just ignore that until you're in like AP statistics or college statistics. For right now, we're only looking for this R value, and they wanted it rounded to the nearest hundredth. That's 2 decimal places. We've got 0.96733, so that would be 0.97. Let's do this, 0.97. All right, so there's our correlation coefficient. Last part of the problem. Explain what the correlation coefficient suggests in the context of this problem. All right, so the correlation coefficient is how well or how strong the connection is, the association or correlation is between the two variables. And the closer this number is to either 1 or -1, the better or stronger the correlation is. The closer the number is to 0, the weaker it is. This is very close to the number 1, and it's positive. So what that means is that there is a strong positive correlation between the number of jumping jacks and Joey's heart rate. I mean, we're not really sure about my heart rate or other people's heart rates, but Joey's heart rate correlates really well to the number of jumping jacks he did. All right, it's pretty much that simple. You could also say that the number of jumping jacks would predict his heart rate quite accurately or quite precisely or whatever. All right, moving on. Geez, Joey, it feels like that problem was just made for you. Made for you. All right, number 34. By the way, that problem had 3 parts to it and it was worth 4 questions. Or it was worth 4 points. 3 parts, 4 points. How's that going to get divvied up? Anyway, let's take a look at problem 34. Hannah went to the school store to buy supplies and spent $16. She bought 4 more pencils than pens and 2 fewer erasers than pens. Pens cost $1.25 each. Pencils cost $0.55 each, and erasers cost $0.75 each. If X represents the number of pens Hannah bought, write an equation in terms of X that can be used to find out how many of each item she bought. Okay, simple enough. Now we know X represents the number of pens Hannah bought, but let's get some other let statements down. We know she bought 4 more pencils than pens, so I'm going to let X plus 4 be equal to the number of pencils, right? And she bought 2 fewer erasers than pens, so I'm going to let X minus 2 equal the number of erasers. Ugh. See it in 3D glasses or something. Okay, so now I can set up my equation. Now it's real simple, right? If I take the cost of 1 pen and I multiply it by how many pens I have, plus the cost of 1 pencil and I multiply it by how many pencils I have, plus the cost of 1 eraser and I multiply it by how many erasers I have, add up all those together, right? I have to get the $16 that Hannah spent. So my equation is going to look like this. 1.25 times X, right? That's the cost of a pen times how many pens there are, plus 0.55, that's the cost of 1 pencil. So I have to multiply that by the number of pencils. Real important to have those parentheses there. And then plus 0.75, that's the cost of 1 eraser. Erasers cost more than pencils, that's fascinating. Times X minus 2, all of that is equal to $16. And there's your equation. Not surprisingly, let's take a look at the second part of this problem. Use your equation to determine algebraically how many pens Hannah bought. Well, that's kind of cool because X actually represents the number of pens Hannah bought, so I'm just solving for X. Now this looks a little bit intimidating because of the decimals, but it's really not too bad. So let's kind of get into it. We'll use the calculator when we need to. So first off, I've got my 1.25X plus, and now I have to distribute. 0.55 times X is going to be 0.55X plus 4 times 0.55. Simple enough, right? Let's go back to here. 4 times 0.55 is 2.2, right? So plus 2.2, then we'll distribute, and that's going to be 0.75x minus 2 times 0.75. I think I'm just going to save some time. That's negative 1.5 equals 16. Sorry about the spacing there. Now, of course, what I want to do is what I always want to do, which is to collect my like terms, collect all my x's. I've got 1.25, 0.55, and 0.75. Again, 1.25 plus 0.55 plus 0.75. No reason to chance it. That's going to be 2.55. So I'm going to have 2.55x. Now I've got 2.2 minus 1.5. Yeah, just again, save myself a little bit of time. That's going to be 0.7 is equal to 16. Right, I'll subtract a 0.7 from both sides. That's going to leave me with 2.55x is equal to 15.3. I'm now going to divide both sides by 2.55. And let's see what we get. 15.3 divided by 2.55 is 6. Now, had a little flutter in my heart there, right? Because you never know, right? You got decimals flying all over the place. Could have made a mistake, right? Now, why do I feel pretty good about this answer? I feel pretty good about it because it's a whole number, right? I mean, look, 15.3 divided by 2.55, that has all the potential to be some ugly, ugly decimal. But it wasn't. It was a whole number. and my answer had to be a whole number because X represented the number of pens I bought. It wasn't the cost of a pen, that could be a decimal, right? It was the number of pens I bought, and that had to be a whole number. All right, let's keep going. We're getting there, folks. Hey, a system of inequalities. Let's take a look at 35. Graph the system of inequalities on the set of axes below. Y is less than or equal to negative 3/4 x plus 5, and 3x minus 2y is greater than 4. All right, great. We could certainly shove these into our calculator, and that might make some sense in terms of just seeing what the graph should look like, but I'm going to do it by hand. Now, the first one's pretty easy, right? Now, the way I want to graph this inequality is I want to think about, graphing, that was weird, the line negative 3/4 x plus 5. Now, we should all feel comfortable with the fact that that is a line, 1, 2, 3, 4, 5, with a y-intercept of 5, and then a slope of negative 3/4, so I'm going to go down 3, 1, 2, 3, and over 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. I can reverse that, 1, 2, 3, 4, 1, 2, 3. All right, and I can get points that lie on that line. Now, I always have this question, should I draw the line in solid or should I draw it in dashed? Well, because the original inequality was less than or equal to, I should draw the line in solid. Again, less than or equal to, that means I should have a solid line. And in fact, I'm going to do this, and I'm going to label that line. Y is less than or equal to negative 3/4 x plus 5. I think you should also be able to label it with just the equation of the line, but that's me personally. Now, I also have to shade. Now, this is y is less than or equal to negative 3/4 x plus 5. Because it's less than, I'm going to shade underneath the line, below the line, right? If this was the roof of a house and you wanted to get out of the rain, you wouldn't be up here, you'd be down here, be under the roof, right? This is the solution set to that inequality. It's hard for me to keep the paper on the screen all at once. Okay, now for the more challenging one, okay? 3x minus 2y is greater than 4. That one's more challenging because it's not already in y equals form. So let me free up a little bit of space right here, and let's talk about 3x minus 2y is greater than 4. I'm going to get y all by itself. I'm going to subtract a 3x from both sides. That's going to leave me with negative 2y is greater than negative 3x plus 4. Now I'm going to divide by negative 2 on both sides, but I have to be very careful because I divided by a negative, that inequality switches to less than. Now here I have a negative 3 over a negative 2. All I'm going to do there is I'm going to make it positive. Remember, a negative divided by a negative is a positive. 4 divided by negative 2 is negative 2. So that inequality now is rewritten as y is less than or equal, y is less than 3/2 x minus 2. So let's graph that, right? I'm going to graph my y-intercept at negative 2. Now with a slope of 3/2, I'm going to go up 3 and to the right 2, up 3 and to the right 2, up 3 and to the right 2, etc. And down 3 and to the left 2, down 3 to the left 2. Now again, I have to do that whole dashed versus solid discussion. Because this is less than and doesn't include an equal sign, we're going to dash the line. Remember, this is a 4-point problem, so non-dashing will lose you a point. We also want to label it. I will do that in a moment. Actually, here, there, I labeled it. All right, and it's less than. I have to shade below it again. Whoops. Well, actually, are you done? All right. Nice and gentle graph. There we go. All right. And I just shaded the inequality. I just graphed the solution set of the inequality. Now, used to be in the old days, they would say something like, put the letter S where the solution set is, or put the letter A where the solution set is. The solution set is where the two shadings overlap, right? This is really the solution set. These are all the points that will solve the inequality, which brings us to the second part of this problem. Is 6, 3 a solution to the system of inequalities? Explain your answer. Well, let's take a look. All right, where's the point 6, 3? 1, 2, 3, 4, 5, 6. 1, 2, 3. This is the point 6, 3 right there, right? It doesn't lie in the overlapped shading. So is it part of the solution set? The answer is no. Right? And explain your answer. Really? Just fit the width. There you go. The answer is no, because it does not fall into the overlapping shading or overlapping solutions, right? It's that easy. Now, one could also argue that another way of doing that, that's really the way they want you to do it. Trust me, that's the way they want you to do it. But the other way to do it is to take the point, substitute it into this inequality, see if it's true, then substitute it into this inequality and see if it's true. By the way, in this inequality, it wouldn't be true. And that's because it didn't fall in this guy's shading, all right? This inequality, it would be true, but to solve or to be a solution to a system, it has to make both equations or both inequalities true, not just one of them. Anyway, it's easier to just say no because it doesn't fall into the overlapping shading. All right, let's take a look at number 36. A ball is projected up into the air from the surface of a platform to the ground below. The height of the ball above the ground in feet is modeled by the function f of t equals negative 16t squared plus 96t plus 112, where t is the time in seconds after the ball is projected. Project the ball, Joey, project it. All right, state the height of the platform in feet. I can't, how about a ball is shot, a thrown, it's projected? Okay, I guess because it's a projectile. Anyway, right, this function, make sure you understand it. This function is giving the height of the ball if you tell it how much time in seconds, right, the ball has been in the air. How long has it been since it was projected? I guess we can't use the word fired or launched. I don't know. Anyway, state the height of the platform in feet. Well, that's pretty easy, right? Because that's really going to be f of 0. Where was the ball right at the beginning? Right? Where was the ball right at the beginning? And that is ultimately, right, this would go away, this would go away. That is at 112 feet. So apparently you are way up in the air when you project this ball onto a movie screen. I don't know, something like that. So anyway, right, that is often what they're looking for here, the y-intercept. Now let's take a look at the second part. State the coordinates of the vertex. Explain what it means in the context of this problem. So because this is a parabola, right, t squared, with a leading coefficient that's negative, right, you know what this is going to look like. It's going to be a parabola that opens downward. It's going to be something that looks like that. And what they want us to find is they want us to find the coordinates of the vertex. All right, and we aren't going to do it by completing the square this time. We're going to do it by putting it in our calculator and taking a look at a table of values. So let's do that. All right, doc, file, new document, no. Let's add a graph. All right, what do we have? We've got negative 16x squared, all right, plus 96x plus 112. Now I'm going to hit enter, and I see some crazy looking graph that clearly goes way up high, and I can't see it because of my window. I do see it come back down, which is kind of cool. And it might be even worthwhile playing around and trying to find a great window. But what I'm going to do is I'm going to actually go into my menu, and I'm going to look at a table of values, and I'm going to get a sense for this. Oh, no. No, 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 no. All right. No, 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 no. All right, so let's get a feeling for this. At 0 seconds, right, The ball is at its platform and is at a height 112 feet above the ground. At 1 second, it's 192 feet above the ground, 2 seconds, 240 feet above the ground, 3 seconds, 256 feet above the ground, and at 4 seconds, 240 feet above the ground. Hold the phone. All right. Do you see the symmetry? 192, 240, 256, 240, 192. There it is. There is our vertex. 3, 256. We can just write that down. All right. It doesn't hurt to show the table, but I looked at the solution set from the state. You can just write that down. 3, 256. So, I wonder where that writing went. Anyway, 3, 256. Now we also have to do that. Explain what it means in the context of this problem. Well, remember, this is time in seconds, and this is height in, I just want to make sure it's in feet. The height of the ball of the ground in feet, great, just wanted to make sure. All right, so how do we explain this in the context of the problem? Well, we say the ball, it was a ball, right? Yeah, a ball. The ball reached its maximum height of 256 feet at 3 seconds. Or after 3 seconds, or something like that, right? At 3 seconds, the ball reached its maximum height of 256 feet. Okay. Now, final part of the problem. Remember, it's worth 4 points and there's 3 parts. I don't know. State the entire interval over which the ball's height is decreasing. Personally, by the way, I think it breaks down as 1, 2, 1, right? 1 point for like the platform height, 2 points for the vertex and its interpretation, and 1 point for the interval over which the ball's height is decreasing. All right, so let's go back to this. All right, increasing, decreasing. Now, let me real quick, let's, I'm gonna take the table off for a second. I'm gonna go into my window. I wanna kind of get the graph here. Now, keep in mind, we don't need, oh man, let me just do this. We don't need any negative x values. I think that's good. But we definitely need to go a lot higher given that the maximum height was what, 256? Let's go 300 and take a look at that, right? So the graph is going, the height is going up, it's increasing, reaches that maximum. And remember, that was at 3, 256, right? So at 3 seconds, this should be a 3 down here. It then decreases this entire way until here. The question is, what moment in time is that, right? We know that this is t equals 3 seconds when it starts to decrease. Let's go back to our table. You can get to your table by just hitting Control T. I wish I would have known that a long time ago. That's cool. Anyway, or not. Let me just trash that. Let's find out when it hits the ground. Oh, look at that. There it is, right? At 7 seconds, the ball hits the ground, right? 0 feet above the ground. So it is decreasing. Its height, it reaches its maximum height at 3 seconds, and then it starts to go down all the way to 7 seconds. So how do I state my answer? Well, they will take a variety of answers on here. One answer they will take will be from 3 to 7 seconds. Look at the red, that's so cool. Anyway, from 3 to 7 seconds. All right, that's one good answer. You could also say t is greater than 3, less than 7. You can even say t t is greater than or equal to 3, less than or equal to 7. You can use interval notation. You can go 3, 7 or 3, 7. All of those would be acceptable. Now, probably some of your teachers have said, well, you can't include the 3 because it's at the actual vertex, in which case go with it. Then go with maybe this one. Do you know what I mean? But the state will take it with the equalities or without the equalities. Doesn't make a difference. I think we might be on to our last problem. Yep, this is a part 4 problem, the last problem of the night. Here we go. So in this particular problem is worth 6 points. And again, like many of the multi-part or multi-point problems that we've seen in the free response section of the algebra exam, it's really a collection of a bunch of shorter problems, all right? It's worth 6 points. Again, you want to get as much partial credit as you can if you don't get the whole thing right. But let's take a look at 37 because we're going to get the whole thing right. At a local garden shop, the price of plants includes sales tax. The cost of 4 large plants and 8 you know what, that's totally irrelevant, the fact that it includes sales tax. Immediately you're like, it's a percent problem. It's not a percent problem. Anyway, the cost of 4 large plants and 8 medium plants is $40. The cost of 5 large plants and 2 medium plants is $28. Now let's talk about this before we even look at the first question. Immediately, you should be sort of smelling something. This smells like a systems of equations problem, right? You bought 4 large plants and 8 medium plants, it costs this much. You bought 5 large and 2 mediums and it costs this much. This is like those problems where you bought 3 sodas, and do you remember the milkshakes and the ice cream cone problem? Kind of like that, right? Except that wasn't a system. Anyway, 2 conditions here, a system. Let's take a look at the first part of the problem. If L is the cost of a large plant and M is the cost of a medium plant, write a system of equations that models this situation. This is about as straightforward of a systems problem as you get, right? Because you do this. You say, well, if I take 4 and I multiply it by the cost of a large plant, and I add 8 times the cost of a medium plant, I have to get $40, right? That's this one. On the other hand, if I take 5 and multiply it by the cost of a large plant, and take 2 and multiply it by the cost of a medium plant, I have to get $28. That's, of course, this condition, right? So you should see these guys a mile on away, right, when they're coming. Now let's take a look at the second part of the problem. Could the cost of 1 large plant be $5.50 and the cost of 1 medium plant be $2.25? Justify your answer. Well, one way of doing it is solving the system and seeing if this is right. But I guarantee if they ever do something like this, the answer is no. Because if it was, then they would have just given you the answer to the system. And the last part of this problem is to actually determine the cost of a large plant and a medium plant. So it ain't going to be this. But let's see how we actually justify that this couldn't be the cost. And really, the way we justify it is see if it makes the system true. So, first thing I'm going to do is check that first equation. So, would 4 times 550 plus 8 times 225, what is that equal to? Well, let's bring out the calculator. And let's minimize it some. Let's bring this all the way up here. Bring the calculator back out. Still don't know why it's not. Nope, that's good. Anyway, so let me just clear this screen out real quick. Nope, that's not it. There we go. Get rid of random marks. Now let's take a look. All right, 4 times 550 plus 8 times 225, and that's equal to 40. All right, awesome, because that's actually what we needed it to be, right? 4L times 8M is 40. Let's try that second one. 5 times 550 plus 2 times 225. Let's see what that one does. And again, let's move this way up so that we can get that calculator out there. 5 times 550 plus 2 times 225. Looks good, except for the fact that I've got 2 pluses there, which I'm betting it's going to get angry at me for, and that's 32. And let's see, maybe the, oh, no, I needed to get 28. So no, don't have to do anything more than that. Don't need to explain it or anything. There's my system. I substituted the point they gave me into both equations and made the first one good, didn't make the second one good, done. All right, so now let's take a look at the last problem. Literally. Determine algebraically both the cost of a large plant and the cost of a medium plant. All right, so in other words, now we got to solve the system. And this is a classic system problem, right? What I want to do is I want to solve this by the method of elimination. And I want to do that by either multiplying both of these equations by something to get rid of the L's, or by eliminating the M's. And I can do that by multiplying this second equation by -4 on both sides. So if I multiply this equation by -4 on both sides, right, that is then going to be -20L minus 8M is equal to 28 times -4, -112. All right, and then I've got my first equation, which is 4L plus 8M is equal to 40. Right, so I took that second equation, I multiplied both sides by -4, and I got this algebraically equivalent equation, and then I just have the first one. Now the reason I did that specifically was because I have these things known as additive opposites here. When I add a -8M to a positive 8M, they will cancel and give me 0, eliminating the 8M's. That'll give me -16L is equal to -112 plus 40. Not feeling like thinking about that right now. -72. Bye-bye. And now I can divide by -16 on both sides. -72 divided by -16 gives me 9/2. -72 divided by -16 gives me 4.5. This is a money thing, so I'm going to put 4.50. So the cost of a large plant is $4.50. Now to figure out the cost of a medium plant, what I want to do is take that 450 and I want to substitute it either into this first equation or into the second equation and simply solve for the cost of a medium plant. I think I'll just substitute it into this equation. So I'm going to have to sneak it in here. 4 times 450 plus 8 times M is equal to 40. All right, real quick, let's do 4 times 450. That gives me 18. 18 plus 8M is equal to 40. Subtract 18 from both sides. 8M is equal to 22. Divide both sides by 8. And let's see what 22 divided by 8 is. This time I'll be smart about it. Gives me 275. And that is the cost of one medium plant. Now, it'd be kind of nice if they had just started the problem and gave us those two pieces of information and just said algebraically determine the cost of a large and a medium plant, and would allow us to kind of like skip all the other stuff, which is just building up to this moment. But they didn't, right? So this is a classic systems problem, right? They give you two pieces of information. You combine them to get equations that kind of look like this. You have to multiply one of the equations, sometimes both of them, by constants in order to get those additive opposites. Add them together. One of the variables cancels. In this case, those were the M's. You're left with just one of the variables, very easy to solve for. Take its value, plug it back up into the original. I need to stop touching the screen. I don't know what it's doing, I swear. And you get the other variable value. And that's it, right? There's just scrap graph paper at this point. And by the way, there is scrap graph paper, right? So if you need a lot of scrap graph paper for no apparent reason, it's there. And then there is some like extra just random scrap at the back of the exam after the formula sheet. And that's good to know because Sometimes you just need extra space. All right, and that was the June 2021 Algebra 1, let me see if I can get all the way back, Algebra 1 Regents exam. It used to say that June 2021. I don't know where this V202 stuff is coming from, but I don't know, maybe it was because it was pandemic or something like that. Many people didn't even take this exam because it was optional. But it was a nice exam. It had almost everything that we needed to see on it, from factoring to solving inequalities, systems of inequalities, both graphically, systems of equations, applied systems of equations, all sorts of good stuff, right? There were probably some topics that we missed, things like residuals, you know, and some other things like that simply didn't come up on this exam. But if you've been working hard and you watched this review, right, then you should be all set for tomorrow. Just a few reminders. You've got 3 hours for the test. Get a good night's sleep. Eat a good breakfast. Seriously, it's important, right? It's 3 hours long. You don't want to be sitting there after a half an hour going, oh my God, am I hungry, right? Get a good night's sleep. Go in there, be prepared, and you're going to do fine, okay? Everybody passes this exam eventually. You will pass it, right? But you want to do more than pass it. You want to do well on it, and you can do that. Take your time. Use your calculator to check things over. Use it creatively to help you solve problems. Remember, we saw things like the store function tonight. We saw solving equations graphically or solving systems of equations graphically. All of that is possible in that 3 hours. You've got all the time in the world. And remember, by 11 o'clock tomorrow morning, you're going to be done with math for like 2 months. And then you got to do geometry next year, which is awesome. I love geometry. I love it. But it's not everybody's cup of tea, okay? Speaking of geometry, on Monday night from 6 to 9 p.m., we will be going over, I think it's the June 2019 or something like that. I don't even remember the last time the geometry exam was given. But anyway, we're going to be giving the last geometry exam. You can find that on the emathinstruction.com website under our blog, the May blog post. At the end, it gives all the exams that we're going over. So Monday night, we're going to be doing the geometry exam. Tuesday night, we're going to be doing the Algebra 2 exam, after which I'm going to pass out and probably just fall asleep on my studio floor. For now, though, I just want to thank everyone for joining. Those of you who joined on YouTube, thank you. Those of you who joined on Instagram, thank you. Those of you who joined on both platforms, that was awesome. So for now, let me just say good night. Good luck tomorrow. Have a happy Juneteenth celebration on Sunday. Remember what that holiday is all about. And we'll see you next year in geometry. Take care, all. And remember, keep thinking and keep solving problems. All right, that's a wrap. And now we got to stop.